Today we're going to be talking about specifically about opacity. We've had reflection, we had transmission, we had refraction. Today we do a little bit of this dull subject called opacity. Why are things opaque? Not really why. What I want to explain is the mechanism of all four of these. How does light work when it reflects, when it goes through a transparent medium? How does it refract, and why or how it produces opacity, that something is opaque. You can't see through walls, you can see through glass. And even if though you see through glass, when you see like through water, well, you get that pencil that you put in the water, it's broken in half, and why does that happen? What's going on there, and so all these issues have to do with how light behaves. And in order to do that, you got to understand a little bit about light, especially what the hell is light? What is this thing we call light? Okay, that's essentially what we need to get wrap our mind around. And the issue here is that we have to contrast what mathematical physics is light versus what we do in this channel, which is the rope model. Okay, there is a difference, a significant difference, I'd say, completely different difference. What does quantum say specifically, but it applies to relativity and string theory as well? Well, they deal with particles. And when they don't do particles, they do waves. And when they don't do waves, they do particles or wave packets. They do discrete one-way mechanisms. Okay, that's essentially it. Because even the wave is taken to be a packet. Okay, the wave, they chop it off. And you say, well, hold it, what came before the wave? What comes after the wave? They chop the wave and they say, here's the wave. And you see it from beginning to end right in front of your eyes. Well, I thought the wave extends all the way to the edge of space-time. So why do they chop it off? Is the wave choppable? I mean, if light comes out of an atom, originates in an atom, and let's assume it's a wave, transverse wave, especially when it travels, because the notion is that it departs and arrives as a particle because that's when you detect it, but in between it travels as a wave, as a transverse wave, okay? Meaning it's transverse motion up and down in perpendicular to the direction in which it travels. Okay, fine. So what are we talking about? What is this wave? Wave of what? And because they never figured it out, they say it's a wave of nothing. That's more or less the party line. And so we're not dealing with physics anymore because now we're talking about a ghost. We're talking about a spirit that is waving. So we need to get a handle on what is light, okay, in order to be able to give you a physical interpretation of how light behaves during reflection, refraction, the transmission in the case of transparent medium, and opacity. Okay, so one fellow says, and this is more or less what most people think out there, this is what they have in the backs of their minds, says something is transparent if the photons, what? Passing through it. Everybody thinks of this photon passing through a medium, okay? Are not fully absorbed. That is, their energy, look at the words he uses, cannot or is not fully absorbed by the electrons in its substrate. It may bend the light. Bend the light? How do you bend the light? Okay, look at the wording, okay? As water does or absorbs certain wavelengths. Absorb a wavelength? What are you absorbing? What is a wavelength? Wave of what? Wave of nothing. So how can you have the wave of nothing? How can you absorb nothing? Okay? It may reflect some of it back. And again, all this is the nonsense that comes from mathematical physics. They learn these words by rote, like poetry, you recite. And we have nothing in front of us because we don't have what is energy? Energy is a concept, a mathematical concept. What is a wavelength? Wavelength of what? Of a wave? What is a wave? What is a transverse wave? Waving of what? Of nothing. And so far we have nothing in this whole so-called explanation, this notion this individual has. And this is what the majority of people think out there who are in physics or mathematical physics. They think, that it's got to do with absorbing energy, absorbing wavelengths. We have the wrong language to begin with. We cannot understand this. And all this is based on the planetary model that you see there, where you see the electron bead, the blue electron bead orbiting the atom. You don't like orbiting? Fine. You can say it's here and there and there. You don't know where it's at. It doesn't matter. All we have in front of us is a red ball in the center, supposedly the proton, and a blue ball on the outside called the electron. So we have one ball next to another ball. That's what you have. You have a tennis ball or a golf ball next to a bowling ball. So what keeps that electron ball bead tied to the proton bowling ball? Why doesn't it fly away spontaneously? Why doesn't it fall to the nucleus? So unless you can explain that, you don't have a model, and all this that this fellow said there falls apart completely. We can't talk about energy. We can't use the word wavelength because we're not talking about anything physical up to this point. Okay? And this is where it starts. We start on the wrong foot. We start with the wrong language. Another fellow says, light goes through the walls of my greenhouse. No, light does not go through, because if light goes through, you're talking about particles or waves. There's no such thing as waves. I guess then that leaves particles. It turns out that according to the religion of quantum mechanics, there are no such things as corpuscles. The so-called particle is an equation, a wave function, or whatever they call it. They got all these synonyms for it, but we don't have a physical object in front of us. So you cannot talk about traveling through. And even if we remove the roof of your greenhouse, light is still stopped by the atoms of air. Light does not go directly to your little plant. It has to go through all this air that's in between the sun and your plant. And people think that light is a little ball that just goes through these gazillions of atoms. Remember, the air covers our whole planet. It doesn't stop here where we breathe. It goes all the way out there, almost to outer space. We have a very thick layer of air covering our planet. Thanks to that, we can breathe. And here's this little photon. It's going through all these atoms of air and other garbage that's floating around there, and reaching your little plant right through the glass in your greenhouse. Man, that's a mighty photon, right? A little photon ball or wave that can go through all these atoms. Okay? Is that what's really happening? And so what do we say to this? Well, we say this, that this is the worldly wisdom. It's misleading intuition. Okay, you think that's what's happening because you think that light is coming directly to your eyes without anything being in between there, and you forget that all that stuff that you're breathing is between your eye and whatever you're looking at. And it's like you're saying, well, it's going right through there. Well, what do you mean it's going right through there? What is going through there, and is it going through there? And so the question is that what Mother Nature does? Okay, and that's why in science, because of this misleading intuition, we don't rely on eyes, meaning observation. We don't rely on hands, experiments, and we don't rely on testimony, meaning evidence. None of those are part of science. Those are all part of religion. In religion, we observe, and in religion, we do experiments, and in religion, we present evidence to convince the jury because we're targeting their belief. In science, we don't do any of that. In science, we do thinking because we're trying to understand the mechanism that Mother Nature uses to do these magic tricks. And so we rely on reasoning, and you have to be able to explain the cause. In other words, make a movie of the mechanism. Only then can we understand what you're talking about, and only then can we visualize the mechanism. You can only visualize a mechanism if you put objects there. Give a simple example, you throwing a stone through the window, and I film it. I show you the film, and you know how the window broke. You say, okay, how did the window break? Well, you're not going to use words like force and wave and energy. No, you're going to say a rock went through the window. And we don't care how strong the window is. We don't care any about all those mathematical nonsense that have nothing to do with the question at hand. I just want to know why the glass is on the floor. And you say a rock went through the window. That's how we explain it in physics. Very simple, baby-like, kindergarten-ish. We understand it. And that's what we need to do with light. The only reason we don't do it with light, gravity, and magnetism, so on, is because we can't see the mediators. That's the only reason. You can't see or touch the mediators. You can't see the mediator of light. You can't touch it. You can't see the mediator of gravity or touch it. You can't see the mediator of magnetism directly with your hand. I mean, you can see it with iron filings. For that matter, I can see the mediator of gravity too, by throwing the pencil, and I say, well, it's gravity. Yeah, but how did it happen? So you can't see the mediator any more than you can see the mediator of magnetism as well. And if we cannot see or touch the mediators, it is useless to go to the lab and do an experiment. You're not going to figure this out through an experiment. We've done all the experiments we ever need to do, especially like for gravity or light. Here's the experiment for gravity. This is all you need to know. That's it. The only experiment. Repeatable. Okay, let's do it twice. Repeatable experiment. You let go of the pen, it falls to the floor. Now you tell me what caused the pen to fall to the floor. And hopefully this is kindergarten stuff. I mean, really kindergarten stuff. Mother Nature is a very simple woman. She doesn't do any sophisticated math. She just deals with objects. You just have to figure out what came in contact, physical contact with the skin of the pen. Once you figure that out, we're done. It's simple stuff. It's baby stuff. That means there's something here that we can't see or touch that is coming in physical contact with the pen. The pen is aware of it, but your hand is not. Okay, that's what we're saying here. Okay, so all we need to do is make visible the invisible stuff. Once we do that, it's kindergarten stuff. It's like if I throw the stone through the window, but you don't see the stone, and I just move my hand and the window breaks, and you say, "How did you do that? That's magic." Yeah, it's magic only because you didn't see the stone. Okay, but if I make a movie of it and visualize it for you, in other words, I show you the stone, and you say, that's stupid stuff. I mean, any kid can understand it. You threw a stone. It's only because you can't see the stone that it's so magical. You say, oh, how did you break the window? And this is no different than that. The only reason you think this is magical is because you can't see the physical objects Mother Nature uses to perform this magic trick. Okay? You can't see what's in contact with this pen. That's it. That's the only issue. Other than that, it's kid stuff. Once you can see that, if Mother Nature or God or the devil, whoever, comes over here and shows you the invisible mediators that they use, that's stupid stuff. That's ridiculous. It's baby stuff. It's kindergarten stuff. The only reason it's magical is you can't see or touch the mediators. No experiment done in the lab will ever elucidate the invisible mediators. For that, you got to drink a beer, sit back, and visualize. Think. Use your brain, not your hands. Okay? Okay, so here we have the waves, and this person thinks, or these people, because there's many of them, they think that these waves go through the walls. And I'm saying, waves, particles, whatever you want, they don't go through wall of bricks, wall of glass, wall of water, or wall of air. So if some of these are transparent, it's got nothing to do with going through. Okay, because for that, first of all, you have to identify the mediator. And you can't use the word wave, because wave is not a mediator. Okay, you got to, in physics, you have to absolutely identify the physical object. Okay, how do we do it with ropes? Well, there it's very simple. You have these ropes, and what these ropes are doing, they're attached to atoms. And so I haven't shown all the atoms here, obviously, and we have a rope attached, for example, to that water block there. It's attached to one atom there, and that atom is attached to another one, and another one, and another one, until it goes all the way to the other side. And that's why you can see through water. Okay? Same with air, and same with a glass window. Okay? So this is what you have to keep in mind. Okay? This is once you identify the mediator, in this case the electromagnetic rope, that's a piece of cake. You say, okay, one atom is attached to another, and one stimulates the other one. You have these torsions going from one atom to another, and now you can see what's happening. What's happening is a relay mechanism. It's not that I can see you directly through the air. It's that whatever light is going back and forth is going through each one of those atoms, from one atom to the next atom to the next atom to the next atom to the next atom, at the speed of light. Why? Because there's nothing really traveling back and forth. What you have is a torsion. If you want to call that torsion travel, be my guest. But it's twirling in situ. And so because it twirls in situ, it can go very fast, speed of light. And because of that, all you have is this whole row of ropes, one attached to the next atom down the road. And I can see the window because of that, because, the rope carries that signal, that torsion, that arrives at my eye. So it's not that I can see the window directly, as these people think, that there's some kind of photon bead, point particle that's coming to my eye and hitting my eye, which is the notion that we've had for 10,000 years now. No, there is no little particle that's traveling to my eye. The reason the mathematicians chose that is it was easier to model, even to this day, their equations based on a pinpoint. They can put what they're looking at is they can model that with an equation that tells them something about position, as they call it, location of that particle, and they say, okay, this particle's here now, here, we measure, we know the speed. That's what they're talking about. But they don't know, it's like I say, they did all this math on fish and ocean. And it turns out that Mother Nature works with eagles, or birds and air. So all their equations are applied to the wrong objects and to the right medium, to the wrong media, okay? You can do all the equations you want. Unless you identify the physical object, all your equations are in vain. Okay? Because again, you might think that there's a little trickle, a little sequence, a little series of particles reaching your eyes, and it turns out that those so-called particles that you're describing with your equation are really a rope torquing in place. Okay, so it's a very different mechanism. And so what is your equation worth if you're applying it to the wrong invisible entity? This is where we have a problem. Okay, and so this is what I like to say, that he who proposes a physical mediator for light has the burden of illustrating the mediator. That's the first thing you got to do, okay? You can't just say a wave did this and a point particle did that. No, please illustrate your stuff first, then begin your talk. If you cannot illustrate, especially your atom or your particle of light, if that's what you're going to propose, or your wave of light, and tell us what is that mechanism or that entity that's there in front of us, if you can't start there, you can't even start your talk. We take the microphone away from your mouth. Okay? You got a lot of work to do. You got to go to your dark basement and brainstorm until you get a physical entity. We don't have an entity yet. You can't do physics. You need an entity to do physics. Okay? In explaining what causes their mediators to travel rectilinearly, if you're going to use the particle model, why does it travel in a straight line? I mean, like I explained a couple of weeks ago, you look at yourself in the mirror and it's straight ahead. And you say, well, is that really true? Well, you can take a laser and run it through lenses, and it's a straight line. I mean, you can do that as scientifically as you want, as they say. You can go to your dark basement and point it at mirrors, at lenses, or whatever, and you'll verify that light travels in a straight line. How is that possible with discrete particles when the entire world, the entire universe is moving? The Earth is moving right now around the sun. I know some people, the flat earthers, don't believe that. But, here you shoot these photons to the moon, the laser ranging, and the Earth moves, so did the moon. And so what, all these particles, travel in curves, especially along warp space? So no, how do you explain rectilinear or straightness with discrete particles? That's one of the things you're going to have to explain. Okay, because light does travel straight. Light never curves around the corner. Okay, and people say, yeah, it does. No, it doesn't. You do it all with straight lines. Okay, you don't have light curve around corners. Okay? And some people don't understand that. That's why, again, people have been misled by their intuition. Okay, that's what they think is happening. Okay, what is a substance causes the mediator to bounce during reflection? Why does that particle come back to you in one case, and in the case of transparency, you continue straight through the substance? I mean, if the photon is going to hit an atom, why does it bounce in one case, reflection? Why does it go through it, transparency, in another case? Okay, and so they have to go through all this rigmarole where they say, well, in one case, it absorbs the energy, the wavelength. In another case, it doesn't. So they have to go through all this mathematical wording that has nothing to do with physics. Okay, we want to see the physical entities. We want to see you illustrate bouncing and going through. Okay, and that's where you got to say, well, the ping pong ball hit the proton bowling ball in the atom and bounced back, and then in this other case, it went through. How do you explain all that? Okay. What causes the mediator to stop, be absorbed, in other words, during opacity? What causes the mediator to go through a transparent substance? Yeah, okay. And explain why the mediator of light swerves and continues to travel rectilinearly through a substance during refraction. Remember, when it goes through water, or sometimes through glass, depending on the substance, light curves, you could say, right? It bends, not curves. It's a straight deflection. And then it continues straight. It's not like it's curving, No, it's straight here and it's straight here. Straight, 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 straight. It's just that it's like bent, chopped, broken at that point. It's not a smooth curve. So you got to explain this. You got to explain how that photon suddenly hit a brick wall and then went off in a 30-degree angle or whatever. That's what you got to explain. And then, of course, they cannot explain that. They just tell you what the angles are. They say, we measured, and we measured the angle, and this is the angle. I don't care about your angle. I want to know the mechanism. So angles is not going to answer the question. Snell's law and so on, not going to figure it out. Okay, so we have one group of people, and they're prominent. They're known as How Stuff Works. I mentioned this the other day. And what they say, it's got to do with more atoms and fewer atoms. And they say light waves run into very few atoms, few of them, referring to the atoms, when they shine through air. So the people here in How Stuff Works, they believe that it's got to do with how many atoms there are. Okay. The more atoms, I guess, the less you can see. Is that the theory? Okay, let's look at this. Let's find out if that's true. Okay. And here we have the situation. Here you are, and you're looking at the window during the day. Okay. And you can see the window perfectly well. There's a sun shining out there, and you're just staring at the window. Okay. So far, so good. Now what happens? Towards the evening, or as the day progresses, suddenly, the sun goes down and everything starts becoming reddish. Okay, so suddenly you don't see the window as well as you used to. And by the time you reach nighttime, you can't see the window at all. Okay, now you can barely see the window. So what happened here? Suddenly the window disappears. Why? Are there more atoms between your eye and the window? Is that what's happened? God put more atoms there at the end of the day? And you don't have to wait till nighttime. I mean, you can do this with a lamp. You turn the lamp off, maybe at night, and everything's dark. You can't see the window. You turn the lamp on, now you can see it. So when you turn the lamp on, there are fewer atoms in front of your eyes from your eyes to the window. And then when you suddenly turn the lamp off, more atoms come in there. Now you can't see the window. Is that what it is? Is that the theory? Talk about Ptolemaic explanations. That's how stuff works. They should be kicked out of science. That's what they should be doing. That's what we should do with them. Okay, so I ran an experiment with my dear wife. And here it is. It's polarization, okay? And when you have these two polarized lenses, if you turn them at 90 degrees to each other, you have opacity. You can't see through them. On the other hand, if they're both aligned, like, horizontally, then the laser runs right through them. Through both of them, you can see the laser at the screen. Okay, so did we put more atoms in between them when we turn them around, or is it, or does this have to do? Does this opacity and transparency have to do with the location of the molecules or atoms or whatever? Okay, so that's the first question for you. Here's another experiment we did, and this one was with tape. You take tape and you turn it around, and it doesn't stop light like the lenses did. These are not polarized. What you have is a tape, a transparent tape. You run a laser through it. We didn't do it too well, and not very scientific, but that doesn't matter. I guess you get the idea. You can do it at home. Just take a laser and point it at two pieces of tape, transparent tape, okay, cellophane, and just put the tapes at 90 degrees to each other, and then again turn it around, and you'll see that it doesn't stop the light at all. Okay, so the fact that you turned one tape 90 degrees to the other doesn't do the same thing as the polarized lenses. Okay, that's what I'm trying to say here. Okay, just in case, we did it with a plastic box that I had there. Okay, and here it is. Let me make this a little bigger. Okay, and so here you have light going through this. You could use glass. You can use, in this case, I had this plastic box, which is handy. And if you shine through this plastic box, you can see it doesn't stop the light. Light, whether you put it at 90 degrees or not, it doesn't become opaque. Okay, that's the point. Okay, but in the case of the polarizing lenses, yes, it does block. It does become opaque just by putting it one at 90 degrees to the other. Okay, so when they're lined up, like, both up and down, light goes through. It's transparent. Suddenly you turn it around, and now it's opaque. It sounds like to me that's got to do with the molecules that make the material. What do you think? Okay, I don't think we put more air molecules between the two lenses because we turn one around. Okay, so this to get you thinking about this. Okay. Okay, let's continue here. Here's polarization according to quantum mechanics. Okay, they say that when you turn it around, and this was Fresnel's explanation, the 1820s, and what he said is, when you turn one of these polarizer or polarizing materials sideways, what you're doing is blocking part of the signal of light. And today, they've improved upon it, and they say, well, you have this electric field and this magnetic field that make up the wave, the transverse wave of light, that we don't know what it is. So they use these words. They say it's an electric field and a magnetic field. Unfortunately, the word field refers to a mathematical concept that just says a bunch of numbers. That's all a field is. And so it doesn't help us much, but we still have a problem. Even if we concede the field as a physical object, we're going to say that it's a physical object. We have one which runs at 90 degrees to the other. Are we saying that by putting this picket fence there, which is what this is called, this explanation, by putting this picket fence, we are eliminating the magnetic field in this example here, and only the electric field is what goes through? Can light be made only of an electric field? Okay, so the vertical in this case apparently chops off the magnetic field. In this specific instance, right, we're talking about a single beam, a single wave. And what these people are saying is that the picket fence, put at 90 degrees to the other one, blocks out one of the components of light, and that's, in this case, the magnetic field, which means only the electric field got through. And what they're saying at that point is that that light that you see there going to the second polarizer, that's only made up of an electric field. So yeah, the question is whether you accept this explanation, because this is what these people are saying. They're saying that only one component of the transverse wave got through. Okay, I think we need to figure out, in order to understand polarization, in other words, right, light goes through it, the two films are transparent, right, and you turn one of them around 90 degrees and suddenly it's opaque. Light does not go through. Okay, it gives us an idea that something's related to the molecule, but then we got to see what these molecules look like, maybe even what the atoms look like. Unfortunately, we only have bird's eye visions of atoms. Some people say, oh, we filmed and we photographed and et cetera, imaged atoms. Only from a bird's eye perspective. Give me an atom, anyone that you want. Look it up through Google, whatever, Google images, whatever. And what you'll find is bird's eye views. You see a ball, bunch of balls. That's all you'll see. Well, that doesn't look very much like a little bead going around. What it looks like is a ball. It looks like this. That's what they look like. This is not a little bead going around. So what quantum proposes for their atom, which is the orbital. What is an orbital? It's a region where you can find the little bead. That's not what you see. What you see is a membrane. You see a ball. Okay? That's the first issue. But even assuming that, you know, we need to know what these atoms look like. Okay? And these are the images that we have. Again, they're not pictures, they're not movies that we filmed. These are images that we make artificially. Okay, and this is what carbon looks like, more or less. They have the little beads going in there. Okay, you'll see that in a second here. The beads are going around because that's the quantum version. But really, the carbon atom looks like membrane. That's at least what we propose, and that's what chemistry uses. Not what physics uses, in other words, mathematical physics, but they use the little bead. But the chemistry and the version we propose are exactly the same in this sense. We're talking about membranes, what you see there. Okay, here's the same one for oxygen. Okay, this is oxygen. Again, they have the little beads going around because they want to talk about electron beads. And what we're saying is that's not what an atom looks like. An atom looks like, you know, the membrane that's on the outside. And those membranes are made out of the threads that make up the rope, and that later on will make up the atom itself. So this is what the atom looks like. That's an oxygen molecule according to us. Okay, so if that's what the oxygen atom looks like, if that's what the carbon atom looks like, what we're proposing, okay, we're going to apply this to calcium carbonate. Calcium carbonate is the material that they use, one of the materials that they use for these polarizing or polarizers, these polarizing materials. Okay, so here's what the atoms look like. Each individual atom apparently looks like. Again, I can't put my hand in the fire. I can only go by what these people have picked up over the years, and it looks pretty much like the ones I'm proposing anyway. So I have no problem with them. And here's what they look like. Here you have the calcium on the left-hand side, and it's a big atom compared to carbon and oxygen. And what you're staring at there is 3 levels of S. You got S1, S2, and S3, which are the balls, the round spherical balls. And within that, you have the p orbitals, which are those extensions that come out of the S shells. Okay, and so calcium looks more or less like that. Carbon is a little simpler, oxygen a little more complicated than carbon, but that's more or less what you have, the constituents of the calcium carbonate molecule. Okay, and when you put them together, this is more or less the appearance of the calcium carbonate. Let me get myself back in here. This is more or less what it looks like. It looks like a little gingerbread man. Okay, you have the calcium on the top. Okay, you have the oxygen atoms, the p orbitals merged with the calcium atom and also with a carbon atom. Two of them, one merged with one and the other one merged with the other. And then you have a third oxygen atom at the other end. So this is more or less what the calcium carbonate molecule looks like. And that's what we're going to be using to build our polarizer, our polarizing material. And it's got to be oriented. Now, I oriented it as a gingerbread man. It could be sideways for all we know, okay? I don't know that. All I can do is go more or less by what we have so far today. Again, we haven't seen the molecule itself. We don't have a photograph of the molecule. So all we can do is speculate and more or less try to visualize what this molecule looks like, okay? So let's build one line of these gingerbread men, okay, these calcium carbonate. And here you see it, okay? This is more or less what they look like. We put one next to each other. Again, I put them in this direction. You don't have to put them in, you can put them sideways for all I know. You know, we don't really know, or you can look at it from the bottom upwards for all we know. I just put them in this direction arbitrarily just to make my point. Okay, there we have a line, okay, this line of calcium carbonate atoms, okay. Let's build a little more. We're going to build a little wall now, okay. Here we see the wall, okay, several layers of this, okay. Let's assume that's what we have in one of these slabs of calcium carbonate, okay? And now we're going to connect them. We're going to connect two of these walls with the ropes. And we're going to just connect one rope because obviously there are many ropes. Imagine each one of these atoms, you have to think of them as a bunch of hydrogen atoms. For each hydrogen atom that constitutes carbon, for each hydrogen atom that constitutes oxygen, we're talking about one rope, okay? So we're just going to put one rope, and here's what it looks like more or less. Let me get this one out of the way, okay? And we're going to put a rope from a source, could be a laser, to that first atom, and from those, you know, you're going to have a series of ropes connecting all these atoms, and then it's going to connect those atoms to the wall behind it, okay? And from there on, further on. Now here they're aligned. You know, the gingerbread men are all aligned in the front with the ones in the back. And so light goes through. It's transparent. The material, these two slabs are vertical, okay, and they're transparent. You shine the light through, it goes right through. Okay, so far so good. Now, what are the possibilities here? What are some of the variables that we're going to look at to try to visualize, understand what's going on in front of us in this magical, invisible, intangible world of Mother Nature's? What's going on in that world? Okay, that's what we're going to try to see if we can visualize it, we can understand it. Okay. That's what I'm getting to. And here is what I think is going to happen here when you switch one of those around, okay? And you can see here they were straight and light goes directly from one slab to the other. Now we're going to turn one of those slabs around, 90 degrees. Look at what happens to the ropes, okay? They're no longer straight. The ones that were going straight, now they're no longer straight. Okay, so I think this is one of the factors you should consider when you analyze what's happening with a rotation of one polarizer with respect to another. And again, what we're talking about here is that suddenly what was transparent became opaque. Okay, do we understand ourselves? Okay, this is what I'm saying. Okay, so just by rotating, all you did was just change the location of existing atoms. We did not put more atoms in there like how stuff works alleges. So it's not like we put more atoms in there. Okay. And those people who say, well, the wavelength was absorbed or the energy was absorbed, well, all we did was switch them sideways. Why would the electrons now not absorb those same photons? So is it a question of just absorbing energy, absorbing wavelengths, whatever wave is? Obviously, there's something more involved here. It's got to do solely when we went from transparent to opaque. All we did was change the location of the atoms. The same atoms, you just switched them around, suddenly what was transparent became opaque. Okay, we got that? Okay, so that's one of the things you got to consider. What's another one? Well, here's my magic rope, okay? And I'm going to do this sideways so that you can see what I'm talking about. Okay, so here we have the rope, okay? And one of my fists is a source, or you could have the polarizer here and the other polarizer over here. As long as they're aligned, they're both up and down, so to speak, then you have the normal torsions, okay? Normal torsions coming from the laser. What happens when you turn one of them around? Okay, that's what we're going to look at. So I'm going to turn one of these around and you can see what's happening. Suddenly you have a quarter wave, quarter link, that's offset with respect to this. Here it was like that, and now when you turned it around, you've got a different frequency, a different link length. Okay, you see what happened just by a 90-degree turn of my hand? Okay, so what I'm saying is these are the things you have to consider when you're looking at least from the rope model, when you're looking at these slabs. One of them is that the ropes are no longer straight ahead. Okay, now this rope is turned with respect to the other rope over there. And the other one is that you're also twisting the rope. Okay, so these are two factors you have to consider when you try to explain, when you try to understand what may be happening in there. Okay, now I can't tell you exactly what's going on in there. I'm not going to tell you that I do know. Okay, all I can do is give you a theory on the one hand, and I can give you on the other hand something to look for, something that you can test with your mind and find out, is this possibly true? That you can rationalize it, that you can reason it. Okay, you can't do that with anything provided by quantum mechanics. Okay, now let me throw another variable here just to drive you nuts, completely nuts. Okay. Here we did an experiment with my son, Hans, and you can turn the slab of calcium carbonate, you can turn it around, and the atom now is in a different location with respect to the first slab. So if both slabs are, like parallel there, and you turn one of them around, whichever, well, what you did is the atoms, the molecules, or the atoms that constitute the molecules, now they've moved sideways. They moved at 90 degrees. So here's the $1,000,000 question. Okay, listen carefully. Can you do that with oxygen, air? Can you do that with H2O, water? Okay, and let me show you the experiment we did with my son. Okay, nobody asked this question in a million years, so here it is for you for the first time. My son turned the water around. Now you can see that little plastic dime there, the plastic coin, and it does move from horizontal to vertical. Is that what happened with the atoms that make up water? Is that what happened with the molecules that make up water? Did they also turn around? Or did gravity continue to pull on those molecules in the same direction, whether you turned it around or not? Okay, let's be more specific so that you see what I'm talking about. Okay, here you have a molecule of water. Okay, let me remove this one here for a second. Okay, here you have a molecule of water. Okay, let's assume that because oxygen is the big atom, okay, oxygen is made up of 8 hydrogen atoms. Okay, it had to be squashed in the sun under pressure to make that oxygen atom. So what do we mean by that? It means that 8 ropes are coming out of that oxygen atom. Okay, but that's not important for what I want to say right now. I just want you to be aware of that. Whereas the hydrogen only has 1 rope, oxygen has 8 ropes. Okay, so that's got to be understood. Oxygen is tied to the center of the Earth, according to the rope model. Okay, so are the hydrogen. We're just going to make an assumption here. Assumption, no proof, no evidence. Assumption. We're going to make an assumption that that the molecule of water is positioned in that direction with respect to the center of the Earth. Okay. So when I turn the water around, okay, and here we're going to turn water around, okay, please bear with me here. Is that what happens to the water molecule? Are we turning it around, or does it remain in the same position as you see it on the left-hand side there? Does the oxygen continue to stay downwards when you move water around? Okay, so this is the question before you. Okay, here's a bunch of water molecules, okay. Is that what happens? Or is this what happens? Look at these 2 pictures. You'll see that there's a little difference. Okay. In one case, water turns around because you turn the whole glass around. In the other case, the water molecules remain in the same direction with respect to the center of the Earth because gravity pulls them in the same direction. In other words, there is no change in the location of the molecules as it is in the calcium carbonate crystal structure. Okay. Hopefully you understood what I'm saying here. That we have a difference between calcium carbonate, which is in a rigid crystal structure. You move it sideways. Now you've moved those molecules, those atoms in a different direction. Does that happen with water? How about with air? Okay, let's look at air now. Okay, here's air. Okay, here's the air molecule. I put 2 oxygen atoms. Okay, so there's your air molecule. Does this air molecule stand up like that? That's the question for you. Okay. You can see that when you turn air around, if you can do that, you grab air and just turn it around. Okay, is that what happens to the molecule? Assuming, the two oxygen atoms are more or less parallel, or I guess, tied to the center of the Earth in a symmetrical way. Can you unsymmetricize them? Can you have one oxygen atom be closer to the center of the Earth than the other? Or whichever way you move your balloon with the air inside it, the atoms in there adjust their position with respect to the center of the Earth, to gravity. Which way is it? Okay. And again, here it is. This is one version, and this is the other version. Which one is true? Okay. I hope you understand what I'm showing here. In one case, the atoms change their location from horizontal to vertical, and the other one, they always remain horizontal. Okay, that's what I want to show here. Okay. So those are the questions for you. Okay. I don't know if you have an answer for those questions, but these are, I think, the things that you have to factor. And one of the things that you can use this for is to destroy the flat Earth. Okay, and flat earthers never listen to. They keep asking the same question over and over. They never listen to the answer, and they just keep asking the same question over and over. They say, "How is it that you can curve water, let alone air?" And so now we have an answer for them. For those of you who are listening, flat earthers don't listen, so they don't know what I'm talking about here. But here it is. Okay. Every atom is connected to the center of the Earth, or to every atom on Earth, so it doesn't matter. But the center is the center of everything. Everything is pulled towards the center. Okay, and here you see it. The water molecules are all pointed towards the center of the Earth. Okay, now we're going to put the ropes in there. Okay, we're going to attach the ropes to all these atoms and molecules. First the water molecules, and now you're going to see the air molecules. Okay, and so now you can see why water curves around the Earth and why air curves around the spherical Earth. Hopefully it's spherical and not a disk, as it is in flatland. Okay, so I'm saying that the atoms have to follow gravity somehow. You cannot isolate gravity from our atoms. I don't care if it's oxygen. I don't care if it's, meaning air. I don't care if it's water. They have to be pulled towards the center of the Earth. And if I rotate my bottle of water, does the water stay like in the case of the calcium carbonate crystal structure, flabs, whatever? Okay, that's the question for you. And that's food for thought, okay, for you to ponder before we can move on to other subjects in the coming weeks. But here's good old Mother Nature, and what she does is she spends the whole day just knitting her ropes, okay?